Hello, in this video we will learn about the second derivatives of functions. And so we already mentioned second derivatives in these videos while talking about the rectilinear motion of an object, especially about a projectile. But here we'll see a little bit more about the formal definition, what it represents, and things like that. But before we do that, I would like to work out an example with you. So let's say we had 3x squared, and we wanted to see how the function looked only using first derivative. So first derivative means getting the derivative of it only once, and the function itself. And so we already know that quadratic functions just look like a parabola. Having the 3 just makes it either wider or narrower. But let's say we didn't know that, and we wanted to see how the shape looked. And so what we would have to do in this case is if we could get the derivative, which we know to be 6x, and then we could set a domain kind of line, and we know that it's 0 at x squared. So when the derivative being 0 means that the slope of the tangent line is 0. What does it mean to be 0? Well, this is the slope of 0, so it means that probably the function goes like this, or like that, or somehow it's either a max or a mean. But that's something to learn a little bit later on. But so, since we know that it's going to kind of turn around, well, most of the times, most likely, that's not for sure, just by seeing that x is equal to 0, you still have to check some things. But we kind of have that idea. But to make sure, we want to see how it turns and if it really turns. So we find the 0, and we know that it's 0 at x is equal to 0, and we want to know how it acts to the left of it and how it acts to the right of it. So if you plug in a negative x, so from here to the left we plug in negative x's, and from here to the right we plug in positive x's. So if you plug in just any negative x, you will get, of course, a negative number, which means a negative slope. And so a negative slope is represented by a downward sloping line. And then if you plug in any positive x, you will get a upward sloping line. And so you can, by this, you can know that your function must look like a parabola going up. And so you could figure this out just by doing this, by getting the first derivative and finding how it acts to the left and to the right of a 0. Of the 0 of the of the derivative, not necessarily of the function itself. It's just a coincidence that in both cases the 0 is x is equal to 0, but I'm only talking about the derivative. However, the second derivative would actually help you know this very, very early on. And so, how do we do it? To find the second derivative of a function, we already know from acceleration, is to get the derivative of a function twice. And I showed you like this, having 2 apostrophes. Another way of writing it is to have this right here. It means exactly the same. It just means the second derivative. So getting the derivative of the function twice. So both of them mean exactly the same, to have d squared times y over dx squared. And having f double prime of x is exactly equivalent. And so if we get, for example, the second derivative of this, we already got the first derivative by getting the derivative once. And then if we get the derivative of the derivative, so d of x of 6 of x, which we find out to be 6, Well, we have successfully gotten the second derivative of 3x squared. So this is actually written as follows. So d square y over dx squared, so that's just second derivative, is equal to 6. And so now, having a positive second derivative, so this is kind of a rule. So positive second derivative means like a u. So whenever you have a positive second derivative, it must look something like this. So I think some teachers like to say up like a cup. So up like a cup. And that's when you have a positive second derivative. When you have a negative second derivative, it's the opposite of a u, kind of like a lowercase n. And actually some teachers say down like a frown. So you can actually see like a frown and kind of like a cup, like so. And so just to keep that in mind, for example, when you have x cubed, which you might recall to be something like this, well, this is actually negative x cubed. And so here, if you were to get the second derivative, you will find that in this portion it's positive, the second derivative, and in this portion the second derivative is negative. So let's try it. So if we have negative x cubed, if we get the first derivative of negative x cubed, we get that this is equal to negative 3x squared. And if we get the derivative of the derivative, so that's the derivative of negative 3x squared, we get negative 6x. And so when you make your line again, like we did, oh no, never mind. Well, yes, we could. Okay, so let's make our line, but now since we're plotting the second derivative, so instead of making the straight line like we did before, like so, we are now going to draw kind of the parabolas we did before. So if we plug in a negative x, we would get positive, so that's up like a cup. And if we plug in a positive x, the second derivative would be negative, so that's down like a frown. And so we know that our graph must transition from a upward, from a cup to a frown. So exactly like we have here.